Afternoon, everybody. It's awesome to be here at a Rust conference. It just shows how much momentum Rust has achieved, and I consider myself a Rustacean like you. I'm here to talk a little bit about Microsoft's journey with Rust, and that journey actually begins with us looking at the problems we've had with C and C++. Specifically, this kind of stat, which is a summary of Microsoft Security Response Center's triaging of the vulnerabilities over the previous 10 years across all Microsoft products. And 70% of the vulnerabilities are due to unsafe use of memory, specifically in C, C++. And we just see this trend continuing. As the threat actors are going after these kinds of problems, it also is causing problems just in terms of incidents as well. I personally find Kernighan and Ritchie C actually a very nice language, and C++ so complicated when you get into all the esoteric features that it's impossible to look at it and understand what's going on. And when I saw Rust show up, I became convinced, just based off its simplicity, its elegance, the fact that it actually enforces correctness, that it was a language that was designed for somebody like me, that likes systems programming, likes the performance, the reliability, and wants a language that actually does what I want it to do. So some of you might have seen this tweet. This is in 2022 in September, and one day I was looking at programming language stats that had just come out, and Python had risen, TypeScript was, I think, on the rise, and I was looking and seeing C and C++ still on that list of commonly used languages. And I'm just thinking, Rust is ready. We should just be switching to Rust. And just in a burst of emotion, I tweeted this. And it just seemed non-controversial to me. But this is my most engaged tweet of all time. It had like 5,000 retweets or 5,500 retweets. You can already see here is just a snapshot as it was climbing in number and count. I actually got a call from Satya Nadella after this tweet saying, really? And I said, yes, really. I'm convinced this is it. And he's like, okay. So Microsoft has been on a journey, not just from my tweet, but grassroots efforts across the company to adopt Rust. And my tweet was just part of a larger movement towards recognizing the problems in C and C++ that has led to things like this, the NSA declaring just a couple months later that people should get off of C and C++ and any other type of unsafe memory languages because of the problems they were seeing in the infrastructure of the US government. So this is an example of one of our first announcements publicly that we were committed to Rust and getting to type-safe, memory-safe languages. You can see here, this is part of our Secure Future initiative. This was an initiative that we kicked off in response to being breached by two nation-state actors. Nation-state actors that took advantage of vulnerabilities like unsafe code to penetrate our infrastructure to get access to emails. And you can see here, this is the company broadly acknowledging that we should get off of unsafe languages. And then we've doubled down on that. We're not just adopting it internally, but we're also supporting the Rust community at large because we know that what's good for us is good for the community and vice versa. So this is a sign of our commitment just financially, and then another sign of commitment is the fact that I'm here supporting the Rust community. So I wanted to talk a little bit about that journey and some of the places where we've got footholds of Rust inside of Microsoft products. It's going to take a while to get Rust everywhere we want it to be. And we're still learning in the process as we adopt Rust. I'm going to give you some of the examples that are the most prominent ones, the most mature ones of our adoption of Rust. And then I'll talk a little bit about some of the feedback, because in getting ready for this, I went and surveyed developers across these different projects and asked them, what do you like about Rust? What do you don't like about Rust? And so I've got that to share with you as well. So let's start with Rust in Windows. And one of the first places that we prioritized Rust is in a fairly small component, but a security critical one. And I think this is a sign of the prioritization we've got for what we go after when it comes to getting off of C or C++ and moving to Rust, and that is security critical code. And this is the UEFI firmware that boots up systems. So we decided to create a Rust version of UEFI. It's called Project Mu. And we did this for two reasons. One, for the firmware in our own data centers in Azure, but as well in our consumer line of laptops, Surface laptops, like the one I'm running here, which has got a UEFI implemented in Rust. You can go and see this Project Mu here because we want the hardware ecosystem to adopt Rust for their implementations of firmware as well. So we've open sourced it and are encouraging our hardware partners to adopt it as well. Another example, and this is more directly changing Windows and getting rid of the unsafe code bit by bit. Our first step into this, we said, what could we start with to see how we can get the code ported to Rust? And the component we picked here is directwrite. Directwrite is a component that is fairly self-contained. It's been a source of vulnerabilities, those MSRC vulnerabilities that I mentioned. One of the problems it's had is this parses fonts, you can see here. And that font parser has been the source of numerous memory problems. So this we decided to do first. And the other benefit of this is that it runs in user space, and it's a separate component from the rest of Windows. So it's a very good project for us to just get our feet wet with. And you can see that two developers spent 6 months and ported 154,000 lines of C, C++ code to Rust. This is about 2/3 of that component and all of the surface area that's been part of the vulnerability surface area of that code. And so we are continuing to port it. And then you can see here the performance impact of moving to Rust. And this is a common theme across everything we've done when we've moved from C to C++ to Rust. We saw a 5 to 15% performance improvement. I'll say that one of the ways that you could attack that kind of stat is say, well, you rewrote it. So whenever you rewrite something, you're going to improve it. And if you'd rewritten it in C and C++, you would have also seen an improvement like that. But the fact is, we did not intend to get a performance improvement. This was purely a porting exercise, and we saw this. Now, and the other aspect of this is that we never see performance regressions either when we're doing our ports. And so this is something else that's very encouraging. And given that we had good success on directwrite, we decided to be a little more ambitious and move into kernel mode. How many of you know about Win32k.sys, the Win32 user and graphics subsystem driver? That driver used to be in user mode in the early days of Windows NT, and it moved into kernel mode. And it's been, I consider it like the underground oil deposit that keeps leaking oil in the form of MSRC vulnerabilities. There's literally like one every month or two, or even more than one every month or two, over the last 20 years. So this is one of the Achilles heels of security for Windows. So we decided to take one of the components, one of the subsystems of it, GDI regions, which are the regions of Windows code, and port that to Rust. And you can see that it took two developers, 3 months, 6,000 lines of code, and this resulted in no performance regression at all as well. So the reason that it took that long, by the way, is the interop between Rust and C, C++. So that boundary, just like a lot of people run into when you're porting a chunk of code that has to deal with C++, most of the developers' efforts and frustrations were spent on that boundary. But nevertheless, very promising results. And so we're going to continue on chipping away at the rest of Win32k. You can actually see if you've got a Windows system, you can go do a dir in the system directory, look at Win32k, and there it is. That's the region code of Win32k.sys sitting there in a file with a _rs, which is the naming convention we're using for Rust modules inside of Windows. Now, another component that we're focused on is security critical code, specifically crypto code. And a lot of you are familiar with Prosimo, the effort that is aimed at getting security critical code ported to Rust. One of the components is Russell's crypto TLS library written in Rust. We've got a crypto engine with our crypto algorithms called SymCrypt, and our first step to support Russells and actually get Russells ready for production inside of Microsoft is to make it compatible with SymCrypt. And so you can see right here, Russell SymCrypt, a provider that uses our SymCrypt library that is available as open source as well, so other people can take advantage of it. But this is specifically for us migrating to a Rust-based crypto stack across not just Windows, but the rest of the company. Now let me switch to Office. And Office has been looking at the benefits that they could get from Rust, not just in terms of memory safety, but in terms of performance. Performance over not just C, C++, but over garbage collected languages. There's a lot of performance critical code in Office that has been written in C#. And one of the things they looked at was if they ported some of that code to Rust, they could actually improve the performance by eliminating the garbage collection aspect of it. So there's an example of not just looking at it for systems code or C, C++ code that can't support garbage collecting, like depending on where it's used, but actually looking at even other areas where Rust can be implemented. One of the first things they tried, and they dipped their toes for Rust, is this semantic indexer and search algorithm. It's called DiskANN for approximate nearest neighbor search. You might have heard of it because it's a cutting edge vector embedding search algorithm. One of the things that they wanted to do for searching what they call Substrate, which is the foundation for Office and all SharePoint documents and OneDrive documents and emails, is to have embedded vectorized based search, but have it perform at massive scale. So the original versions of this algorithm did really good at order 100, order 1000 kind of vector searches. They were looking for order 1 million searches, and so they decided, working with the Cosmos DB and the Postgres team at Microsoft, to create a Rust implementation of this algorithm that would scale to those numbers and have high performance and contribute it to Cosmos DB and Postgres. So DiskANN is actually built in as the vector search engines in those databases that we offer in Azure. And here's what they achieved with it, with the port. You can see here 2 lines. This is recall, and this is queries per second, and what they found is dramatically improved performance for the same query per second on recall over the C++ version. So right there, a huge win. And over on the right side, you can see that even the memory footprint went down in the Rust version compared to the C++ version. So massive win for them on this one, and encouraging them to continue on in a Rust migration and adoption of Rust inside of Office. Now let me switch and talk a little bit about Rust in Azure and my home territory. One of the things that I did even before that tweet was say no more systems code in C++ in Azure. And I did that probably 2 or 3 years before that tweet, because I was already like, enough is enough with this. Rust is ready, let's just start using Rust and not create more debt for ourselves. And this is a tour through some of our adoption of Rust inside of Azure. One of the first things we did, and we started this effort a few years ago, was to try to get an industry standard open source root of trust for our cloud servers. The root of trust is what provides the trust for the whole system. It's what measures the code, it's what has policies for what firmware will run and produces an attestation for what that code is. This project is called Calyptra, and we started this project with other hyperscalers as well as some of the other hardware vendors out there. And this has become, since we started it, been contributed to the Open Compute Foundation, and now is part of a standard part of hardware coming out of a bunch of companies, including AMD and NVIDIA. But of course, this being very security critical code, we decided together as a group that we would implement it in Rust. And so the emulator, the firmware, the ROM for this are all written in Rust. It's all open source, so you can go find this too out on the web. So this is literally at the heart of Azure's servers. And then another security critical component, one that we announced just in the fall, is called Azure Integrated HSM. So we've got hardware security modules in Azure where we put our root keys and other sensitive secret keys. But those keys many times have to be distributed to applications for them to use them. And one of the things that happens when you distribute those keys out of those HSMs is suddenly they're not in HSMs or protected by HSMs anymore. So as part of our effort to improve security of the platform, even before SFI, is to try to keep those keys out of the hands directly of any application. And the key to that, pun intended, is to have an HSM sitting inside of every server. An HSM that the main central HSMs can talk to and distribute keys securely into, and then the applications on those servers get access to use those keys, but they never see the keys, and they can't, nobody, if they got on that server, can copy the key out and use and share it or distribute it. This hardware HSM is literally going into every server that we're deploying starting this year in Azure. So we'll effectively have a distributed HSM fabric based off this, and if you can see where this is going in terms of how we implemented the firmware for this, it's written in Rust. And another place, and this is one where that edict of no more systems C++ or C code really had the biggest impact on Azure's development, was with respect to our hardware offload. So like other cloud providers, we've got a hardware offload card. That hardware offload card is running ARM processors separately, and that's where we have storage and network processing happen off the main server cores. And this is a place where we've got agents for networking and storage as well as agents to support the management of the server. Many of those components had originally been written in C and C++ because this is system code, can't tolerate garbage collecting for a lot of those kinds of functionality. So I declared a few years ago, in whatever authority I have as CTO, to say no more C, C++. To my pleasant surprise, all I had to do was say it in a few meetings, and suddenly it was like the rule, the law of the land. And since then, we've had no more C, C++ components. The new components have all been in Rust. And in fact, several of the component teams took their existing C++ code and migrated it to Rust. So this is the core of the Azure foundation now being built on top of Rust. And then when it comes to the hypervisor that runs to support the virtual machines in Azure, that's another place. Hyper-V you're probably familiar with. Hyper-V is our hypervisor. It's written in C, C++. And this is a place where we decided to get our feet wet with Rust by taking a tiny piece of it, specifically the ARM64 emulation code in the hypervisor, because we've got ARM64 servers of our own that we're deploying now in Azure. And so that effort to get Hyper-V ported and supporting them started several years ago. That part of the hypervisor is written in Rust. And we're converting more components to Rust. The Hyper-V team is all in on Rust. And the Hyper-V team's not responsible for the hypervisor, but para-virtualization as well. And this is just from a few months ago. We open sourced, maybe a month ago, we open sourced something called OpenVMM, Open Virtual Machine Monitor, which is a para-virtualization virtual machine monitor that is written in Rust. And this is what we've got running underneath our virtual machines in Azure that are using our new networking stack, because that's where the networking driver support is implemented inside this for compatibility with legacy operating systems that aren't enlightened to use the new networking stack. So again, another place where we said, you know, traditionally we would have done this in C, C++, let's do this in Rust. And then this one I think is really cool. So this started as somebody that I know in the security team of all places that one day came to me and said, I've got a cool demo to show you. So we have the meeting, and he shows me launching a virtual machine, a tiny virtual machine, in literally microseconds. And in that virtual machine is nothing more than a piece of code that says hello out to the hosting program that launched it. You know, we think about virtual machines as being big, heavyweight things that, you know, you run full-blown operating systems and they take at least tens of seconds to launch. In this case, a few microseconds, not to run an operating system, but to run just a fragment of code. And we said, wow, this is really cool, because what we can do with this is launch WASM inside of hypervisor protected sandboxes at the speed that WASM needs to be launched at when you have things like user-defined functions or network virtual functions that are small, need to be isolated, and are embedded inside of a system where getting out of that sandbox would cause a security problem. And you can put multiple customers next to each other, just like we do with full-blown virtual machines. So thus was born the Hyperlite project. And the Hyperlite project, we open sourced just recently, completely written in, well, it was prototyped in C#, so when he showed me this demo, he had done this in C#, and it's just using Hyper-V APIs. It also supports KVM as well. It's written in Rust. And you can see here, there's a blog post on it from just last week, Hyperlite achieving 0.0009 seconds launch time for a virtual machine, and supported by the implementation in Rust. Now, going further up the stack into the service space. So we have something called Azure Data Explorer. This is our logging analytics platform. And this is what we use at Microsoft just for our normal analytics. Monitoring, you can see petabytes of data that ingests every single day. We've got billions of queries executed by Microsoft as well as our customers that are using Azure Data Explorer. And one of the things that that team decided to do after version 2 of this a few years ago was say, hey, we need to have this thing scale, and we want better security for this. Let's go and do it in Rust. So this is another component where they went and implemented this thing in Rust, and this is a total of 350,000 lines of code that they wrote in Rust. So a team that just got very deeply into Rust, and the results are fantastic. I mean, better performance than the C++ version. Obviously, it's all safe code because it's one big component. And so they were just thrilled with this and served as a poster child inside of Microsoft for look what you can do with Rust. And then finally, in my own team, I've got an open source incubations team that's focused on cloud native incubation. So if you've heard of Kubernetes event-driven autoscaler, Kata, that came out of that team. But one of the projects that we're working on right now is a reactive, it's kind of a new category of data program, data service, where you can basically have standing queries that are configured to respond to particular conditions. So if you think about a database query and you say, show me all the results with these conditions, here you set up a standing query that says, when these conditions are satisfied, fire this event. So it's instead of polling something, you can just basically database query off of a change feed coming off a database or some other system, and then have this Drasi look at the state changes and understand when that query is satisfied and fire. We prototyped this in Node, and then we decided to, at that point, that the incubation was promising. We wanted to make it open source and available to customers to try out. So at that point, we said, it's a systems piece of code, can't tolerate garbage collection, we want high performance for this. Let's go do it in Rust. And so that's open source that you can find Drasi platform completely written in Rust. And then finally, this just coincidentally came out yesterday. This is the blog post from yesterday, Rust in Time, announcing the Azure SDK for Rust beta. So Rust is not just being used inside of Microsoft, but now just because of customer demand, is a first-class language for Azure's SDKs. And the beta version of that just came out. So how about that feedback? What have we been hearing from people? So a lot of the things that you probably imagine and the reasons that you're here. Memory safety related vulnerabilities reduced, data races reduced friction, more time to innovate. That's my favorite at the top, and I hear that one a lot. If it compiles, it works. Unlike C++, which it compiles and who knows what's going to happen. So now how about the downsides, the negatives? Number one, C++ interop. And that's probably not a surprise. I think that's been a topic of conversation here. The tooling is still behind. There's no, when people are looking for functionality, the crate ecosystem is a little bit immature and people are unsure what crate they should be using. What are the good crates? What are the approved crates? And even in Microsoft, we're still figuring out what crates we should be using. Some features that we rely on haven't stabilized. The language is still evolving. Dynamic linking, which is very common in Windows ecosystem, is a problem with Rust as well. So not all rosy, but the fact is rosy enough that we're just all in at this point, even given this. And I'll tell you the other thing that people ask is, well, how do developers that are used to doing C++, how do they view the switch over? My own Drasi team, for example, had never tried Rust before I said, let's go do this in Rust. And I came back to them and I check in, how are things going? Well, it's really hard. It's memory management and the borrow checker, it's just complicated, I don't know. 2 months later, they're like, I love it. And that's very common too. It's like 2 months in and people flip from, I don't get it, to I love it. And that's been a common theme as well. All right, so let me leave you with a little bit of forward-looking what we're working on at Microsoft. Because we love Rust so much, we want to figure out how we can move to Rust faster. And there's 2 areas where we've been focused on moving to Rust faster. One is a very niche area. So I mentioned our cryptographic libraries. This is if you get screw that up, you're in big, big trouble. So one of the things that we've got in my own research team is verified crypto. So we've been developing verified crypto algorithms, including for post-quantum crypto. And we want that to be adopted inside of Microsoft and even make it available to the world. So one of the things that we decided to do, given that we'd already had verified crypto versions in C and C++, is to port them automatically to Rust. And what that would allow us to do is just take all of those man years of effort and just adopt them in Rust where they're already verified from the C. And that verification carries forward. So now we have verified Rust crypto libraries. And so Jonathan Protsenko and Americ Formhertz, Jonathan's on my team, you can see there at Microsoft Research, worked on a transpiler. And I've got a demo here of the transpiler transpiling the Cha-Cha-20, that's a funny name, but it really is Cha-Cha-20, crypto algorithm that we developed. It's verified crypto from C to Rust. So here's the code for the Cha-Cha implementation in C. One of the things that you'll notice when you look at crypto code, it's just lots of byte level manipulation because that's what crypto operates on. And if we scroll down here, I'm just doing this to get a flavor for what kind of code that this transpiler handles. Because the caveat here, and here's the transpiling to cha-cha.rs. And if we go open that cha-cha.rs, you can see here, looks similar. And there's side-by-side comparison. And we'll just go down and find one line of code here where you can see there's a text plus I. So this is scary when you're doing this in C. And over here is the Rust version of it that the transpiler created. So this is all 100% safe Rust code in this transpilation. And then you can see here there's a test. So after we transpiled, here's the test code for the plain text and the ciphertext that should come out of that algorithm. And there's the encryption of that input of plain text. And if it matches, you can see there's an assertion there. If it doesn't, it's going to say success. And so here we're going to run the test and success. So that's the transpiler, and that's great. So now we can take advantage of Rust for that verified crypto code without having to go re-implement it and have it be re-verified. The transpiler is very narrow, though. I mean, the C code has to be very strict, fit within certain guidelines for the transpiler to work on it. But we're more ambitious. We want more automated translation of C and C++ to Rust. And we're just getting started on this. And guess what tool we're using to do this or try to do this? You talked about it in the last session, the LLMs. So generative AI, what can it do? Well, so to set this up, one of the things that we've been working on at Microsoft is something called GraphRAG. So if you're familiar with the retrieval augmented generation, this is where you go and index, just like I was talking vector and embeddings, a data set, and then you do lookups based off of the prompt that the LLM is being asked, to respond to. You fetch the appropriate documents with the closest match, like the disk ANN algorithm would find. And then you feed that into the LLM, and it can answer the question grounded in that data. But GraphRAG takes this a step further because it does hierarchical RAG. So it has embeddings at different scopes of abstraction in the documents. And we find that this allows for much more precise location of relevant documents and fragments of documents than just simply a flat vectorized database. And so where this becomes relevant is when you're translating code. Because let me show you what happens well, here's what code would look like with GraphRAG, where you've got higher levels of abstraction for the whole program, then for functions, and then for pieces of functions that are all being indexed. And this allows for different scopes to be retrieved through this GraphRAG mechanism. And like I said, where this becomes relevant is when you just try to translate a flat piece of code using an LLM. And how many people have tried, given an LLM a piece of C or C++ and said, go translate this to Rust? So some of you have. And the results are pretty mid, aren't they? But what the GraphRAG translation process does is it creates an abstract syntax tool tree. It creates this hierarchical graph from it, creates the embeddings and the code summaries, and then gives that to the translation engine, which then goes and starts to chunk away at the translation at the different scopes. And I want to show you our first kind of example of this just getting off the ground by translating a simple demo game that is written in Python. So here's the game. It's a simple platform jumping game. And you can see it consists of a bunch of files, which already, that's a problem for LLMs because LLMs just like everything in one prompt. So you can see here we're just flipping through the different files, obstacles, here's the main game file. Now let's give this to an LLM. Well, first, actually, let's first run this. This is the Python game just being run. And you can see simple platform jumping game. The next thing we're going to do is just give it to GPT-4o and say, translate this to Rust. So first, we got to just copy all those files into one big long prompt and then paste it into the context and then say, translate this. And here's the translation, main.rs. So let's go see. Well, already it's got a bunch of problems with the code. Now let's go take it and translate it with the GraphRAG-based translator, which you don't need to chunk the code. You don't need to flatten the code into one file. It's going to go translate, work on every individual file. Here's the ported code in Rust. The same files that we were just looking at. There's obstacle. Here's the main file. There's a whole 100% safe Rust. And then the real test is, does this work? Does it work like the original? And there it is. So that's just a taste I wanted to give you of Microsoft's journey into Rust. You could see it across Windows, you could see it across Office, you could see it in Azure, and you can see how we're focused on trying to make it easier to port existing C, C++ code to Rust. The faster we can get off of C, C++, we think the better. And it's, like I said, it's really exciting to be here and see all this momentum behind Rust because this Rust community is what makes a language popular. And people will come and say, hey, wait, there's this new language that's even better than Rust. It's more easy to use than Rust. And I say, well, when's it going to be ready? Because we're over 10 years into Rust, and we're finally ready. Because it takes a long time for a language to mature, for the tooling to mature, and we're not even finally, completely done with maturing the Rust toolchain. But anybody that wants to come along at this point and disrupt something that's already as good as Rust has a very high hill to climb. So I don't see anything replacing Rust anytime soon. If we can get things to Rust, then what's the point? And so we're 100% behind Rust. And again, want to thank everybody for coming, and thanks for inviting me to come and to give you the closing keynote. So with that.